In this video we're going to be having a look at Karnaugh Maps, and Karnaugh Maps, also known as K-Maps, are a graphical technique for simplifying Boolean algebra, sort of, or normally logic circuits, and if used correctly can provide the true minimum. Now they sort of have an upper limit of max 4 inputs. Right, so if you're using for larger systems, okay, I'm not aware of any strategy that easily allows you to do that. Perhaps you can, but really you'll only want to use them for 4 inputs, if even that is getting a little bit on the larger side for these. Okay, if you've got large circuits that you're trying to simplify, you're best using the Boolean algebra simplifications that we covered previously. But let's have a quick look at how they work. So a Karnaugh map for a 2-variable system would look something like that. Right? Not very complicated, and you would fill in from the truth table the contents of it. So in this case, if we've got A, B and Q, 0, 0, 0, 1, 1, 0, 1, 1. Alright, the values that are in the Q column, so let's just say it's 0, 0, 1, 1 for example. Okay, where we'll make this row 0, this row 1, this row 2, and this row 3. These are placed into the K-map, or Karnaugh map, based on the values of the inputs. Okay, so A is 0, so we're on this row here. This is the A side with the 0 row, and B is 0. This is the B side, and B is 0, and 0 goes in here. And so I'm going to write the little bottom right hand corner here. I'm going to show you which row that's associated with. A is 0, B is 1. Okay, that would be 0 as well. That would be row 1. A is 1, B is 0. This time we've got a 1. That's row 2. And our other 1 goes in there as well. Now the way these work is, let's say I was to write the Boolean algebra expression for this. A and not B, or A and B would be the expression. Now we should be able to simplify this using Boolean algebra. Obviously this goes to that, which equals that, which equals A. But let's see if we can get the same result using a Karnaugh map. And the idea in the Karnaugh map, there's a few rules, but the idea is to circle the largest number of ones provided the circle group, okay, it doesn't have to be a circle so much, the circle has 2 to the n ones in it, where n goes from 0 to infinity. Right, so, but practically you're never going to have probably more than 4, n being 4, but it can be. So for example, you can circle e.g. 1 times 1, 2 times 1, 4 times 1, 8 times 1, and so forth. Ones must be adjacent, so can't include zeros at all in your circle. Okay, it must be rectangular. Okay, so no odd shapes. We really are making circles or rectangles here. You can't sort of have blobs that sort of take only some of them. Okay, that's not alright. But there are a few things that you can do. You can overlap around the sides, which I'll show you shortly. But basically, we're going for the largest number of ones, alright, trying to circle them. So in the example we've just done, I would circle these two here. Right, they're next to each other. Alright, so they're in adjacent cells, there's no zeros. They're a group of 2, so it meets this rule here. And then I would read off the simplification by looking at the inputs on the outside. And the way I say this is that, well, A must be equal to 1 for both of those ones to be true. So I can say the output A has to be true. For B, well, B could be 0 or 1. So we're covering both possibilities. It doesn't matter what it is, so we can drop that one. Alright, if B is 0, it's on. If B is 1, it's on as well. So B plays no role in determining the output of this circuit. So from the Karnaugh map, we would get Q is equal to A. Right, so once again, A must be equal to 1. Okay, we're not interested in this row, but B could be any value. So as far as we're concerned, we can drop B. It's playing no role here. And you'll note we get the same example that we would have got from Boolean simplification. Alright, let's have a look at a slightly larger system. So we're going to go back to our majority counter. Alright, so remember we did the sum of products and the product of sum forms. Well, the sum of products form, we're going to write this one out again and see if we can then simplify it. Right, you could do this using Boolean simplification, but let's do it using a K-map and see how we go. So let's just draw the truth table again. 3 inputs, S3, S2, S1, and our buzzer. We'll quickly fill this in. Oh. Of all possible combinations, and then remembering the rule of how this circuit worked, if 2 or more are on, then the output is high. Alright, so 3 zeros, 1, 0, 3 ones. Make sure we got that right. 3 zeros, 1, 0, 3 ones. Good. So let's draw this as a K-map. Now there's actually 2 ways that we could do this. We could draw a horizontal one, or we could draw a vertical one. Right, it doesn't actually matter. And you can put your inputs in any order you like. Also is not going to change the answer. What it may change though is how easy it is for you to fill in the K-map. So think carefully about which way you want to be able to fill this in. On the outside, we're going to put in numbers again. So in this case, 0, 1. But note carefully what happens when we've got 2 inputs on one side. 0, 0, 0, 1, 1, 1, 1, 0. Now, be very careful in noticing what I did here. Note that this is not counting in binary. The way K-maps work is that between each row or column, only one input can change. So from here to here, I can't jump from binary 1 to binary 2 because both the first and second bits would have changed. So we actually go to 3 and then 2 if we were reading it in binary. Okay, so the same thing would have happened here. Okay, and 0, 1 there. Very important you remember that when you're drawing a K-map, right? Otherwise it will not work for you. Filling these in, if I was to label them again, my 8 rows. Okay, so I would be filling them in by going 0 there. Okay, so S3 is 0, S2 is 0, S1 is 0, we're in here. S3 is 0, S2 is 0, S1 is 1, we're in here, and that would give us that one. Note that we then jump. Okay, so we've now got a 1 here because we're in row 3. So you can't just read down the table and fill this in because of that change in the way that we have constructed the truth table versus the K-map. Okay, row 2 would go in here. Okay, row 4, S3 is equal to 1, S2 is S1 equals 0, gives us a 0 there. The remainder are all 1s. Let's just label these 4, 5, 1, 0, 1 is 5, 7, 6. And that's how we draw it as a horizontal truth table. Oh, sorry, K-map. Same thing again, if we were to do this as a vertical one, okay, nothing changes. We're still going to get a similar pattern. But let's have a look at how it would be. In this case we've got S3, S2, S1, so we've got this first row again. Up to you which way you go at this point, but I think I might go down this way just to be a little bit interesting. Next one I've got is row 2, also equal to 0. Next one I've got is row 6, which is a 1. And then I've got row 1, 0, 0, row 4, which is a 0. Okay, so this was row 0, 0, 1, 0 is row 2, 1, 1, 0 is row 6, and 1, 0, 0 was row 4. 0, 0, 1 will give us row 1. 0, 1, 1 give us row 3, which was a 1. 1, 1, 1. Row 7, 1, 0, 1 will give us row 5. And that will be 7 there. Alright, so in both cases we've actually ended up with the same pattern, even though we've drawn our K-map in different ways. And I could have reordered the inputs and still come up with something similar. I'm now going to circle my groups. Now note, in both cases I've got the same number of groups. Okay, so I'm showing you once again that it doesn't matter which way you orientate it. But also note that I don't just circle this guy by himself because we've got these two groups. Okay, that's not a good way of using these. You will not get the simplified version, the fully simplified, if you do that. You are always going for, remember, the largest number of ones, provided you can meet those other rules. So we go for groups of 2 where possible, even with an overlap, that's fine. Okay, overlap is fine, no problem. So now let's read off from this K-map the simplified expression. So the buzzer is equal to, and let's do the vertical one here first. And this one I see S3 could be 0 or 1, so it doesn't matter what S3 is, but S2 and S1 both have to be equal to 1. So S2 and S1 both have to be equal to 1. Or, let's have a look at this one here. S3 must be equal to 1, but by the looks of it, S1 has to be equal to 1, but we don't care what S2 is. Okay, S2 could be 0 or 1, who cares, so we can drop that one. So S3 or S1, or, and we'll do the final one here, S3 has to be on but we see that S2 must be on, but S1 could take on any value. So from the expression that we had here, which was looking quite long and complicated, all right, we needed 4 3-input AND gates and 3 NOT gates and 4-input OR gate and so forth. We've gone to a 3-input OR gate and 3 AND gates. So much higher reduction for the same exact functionality, and this is where this is quite useful. Alright, and you might say, well, what happens about this row? We haven't got that anywhere. Okay, if they're all on, well, if they're all on, all 3 of these will be true. So we still get the same functionality, and that's how the simplification was made. We can read off the same simplification here, it would just be in a slightly different order. So if I do the horizontal one, I'll get this term here. If I get the top vertical one, I will get the first term. If I do the bottom vertical one, I'll get the second term. Alright, so good to be able to check that. Final thing I want to show you is a 4-input Karnaugh map. So in this case we might have 0, 0, 0, 1, 1, 1, and 0. Just remembering that it's not in binary. I just want to give you a few examples of how you might circle things if this was your Karnaugh map. Okay, so in this case we could quite easily, I might just copy this so we can use it again later. In this case you might say, oh, we can just circle these ones. Well, yes, that is a simplification, but that's not the minimal simplification, because we can overlap over the edges. Alright, so these then fold over on this side and come around back on this side, resulting in an expression where we see that, well, we don't care what A or B is, every possible combination, C or D, we see that C and D must be equal to 0, 0 or equal to 1, 0. So in this case, it doesn't matter what C is, D just has to be low in order for the output to go high, and that will give us the same as all those ones. Alright, let's have a look at another example. You might say, hold on, there's nothing I can do here. Well, once again, we can overlap over the edges. Alright, and in this case we can see that what would be the condition here? B has to be equal to 0, because it doesn't matter what A is. And looking in the C and D columns, we see that D must be also equal to 0, while C could be 0 or 1. Doesn't make a difference depending on which one we're in. Alright, so the rolling over the edges is a tricky one just to watch out for. Other things that we can do to make it a little bit trickier for you, and these could be real problems that you're encountering. Okay, you might go, oh great, I can circle this one. Well, no, because 6 is not an even power of 2 to the n. Alright, so we cannot do that one. Instead, the best solution is something like that, with 2 overlapping groups of 4. And that's perfectly reasonable. Finally, if you end up in a situation where you have, let's say, something like this. Obviously there's a group here and you go, oh, I can't make a group of anything with 2 or more in that, I can leave it. Well, no. Even if there's only 1 by itself, you must include it. All right? Never can you just leave a logic 1 by itself and not circle it. All right? Unfortunately, it does end up making this expression more complicated. So we end up with something that's nice and easy for not A, not C in this case. Don't care what D is, don't care what B is doing. Or, unfortunately, the full expression involving all the inputs for that particular 1 by itself there. And that's fine. That is the minimal solution. But you will always strive to be able to circle them into the biggest groups as possible to solve this problem. And we'll just quickly do this one as well. So the top box here, we would get not a D, or bottom box here, we would get B, D. So, quick summary of Karnaugh maps. Okay, they're a graphical technique for simplifying the Boolean algebra expressions, or the logic circuits, depending on what you've started with. Generally, we say it's a maximum of 4 inputs. Okay, you can use them for larger, but generally that's where they're most useful. We did the 2 by 2 system, so with 2 inputs, square with 4 in it. Showed you how to take it from a truth table into the K-map. Gave you the rules, circling the largest number of ones possible, provided that it's, 1, 2, 4, or 8 ones, okay, or 16 if you manage to get all ones. You can't circle diagonals, right? So in no case can you go diagonally across ones. That's not allowed. They always must be adjacent, but you can roll over the edges. That is fine. All right, and no odd shapes, and never forget a 1. Never leave a 1 by itself. Where to look between the 2 different ways of doing 3 input, whether you do it vertical or horizontal, we still get the same solution both ways. And just remembering that once we've got 2 inputs on one side, the way you count it is a bit trickier. All right, it's not in binary. 1 bit can change at a time only. And then when we look at 4 by 4 systems, we saw there's a few anomalies, a few more interesting ways of how you would circle things, but still following the same rules.